All right, everybody, welcome on in. We're looking at the, let's see, this is the 18-week full term, full semester stats class. So welcome on in. Remember which class this is this time. So couple things to look at. Okay, so since the last time I was in here and I was encouraging people to take that survey, it looks like we had 2 more people take the survey. We really need to do better than that. So I guess it's possible that about 9 people just sort of vanished and just dropped the class. We're kind of getting to that point in the semester where sometimes people's initial motivation of going to college and taking a math class, and they're like, no, I'm really going to do it. We're reaching that point where sometimes that starts to wear off a little bit and people start getting tired. And let me make sure this is muted. Yeah. And then sometimes people just have real issues going on, right? COVID is messing up a lot of people's lives. Work is a problem for some people right now with COVID, and taking care of either little kids or older parents and stuff like that is a problem. So it's possible we just lost a bunch of people. So what's going to happen is I'm going to release the data on today's Tuesday, right? So Thursday, no matter what. Whether more people sign up for the survey or not, at some point we just have to release the data because I need you all to be able to work on your projects. But it is in your best interest to make sure that if you have not done the survey yet, do it. Okay, I know it might seem like, why is he so concerned about trying to get 9 more people to take the survey? Well, 25 is, I would call it insufficient, right? It's definitely going to make it more challenging to do your work. Your histograms are going to be a lot rougher, and you're going to be trying to decide, is that normal? I can't tell because we don't really have enough points, right? So if you only have 25 points, 9 more is actually a lot more. That's like 30%, right? So if you can increase by 30% and go from really what is insufficient data, which it'll work. You guys can get your stuff done. But really, it's going to be harder to do. If you can get that 9 more, that 30% more people, it's going to be on the lower end of easier to deal with. So, it will make a big difference if we can get some more people in there and signed up to take that survey, so that we can move forward with that stuff. So if you're one of those people that keeps forgetting, just go do it now. Just go. If you've forgotten to take the survey, I know it's one of those things. Like, you come in here, I tell you to take the survey, and then class ends and you have to go to work and you do these other things. And since it's not an actual assignment, you forget. Just go take the thing now while we're having class. Okay, if you're one of those people, that would actually help the class. And I know it's hard because it's not worth points. Again, we're trying to make sure we protect people's privacy because we don't want anyone afraid to answer certain questions. And it's just better in general if you can keep people's privacy safe from those kinds of things. But then you have to, we have to make sure that everyone goes and does it, even though there's not, a big motivation in school is points. Big motivation in life is money. Sometimes you do things even if you're not getting points or money. Right. Even even fake points, like fake internet points. How many of you run around doing stuff because you want some fake internet points? You want some likes on Facebook, or you want some upvotes on Reddit, or whatever it is that you're doing. You're not gonna get any kind of points here, but you're all a group of people that banded together and got something done because you all have similar interest, which is to get your data so that you can start working on your project. So if you have keep forgetting up to this point, or if you've just, whatever, you don't have a good attitude about it, please go in there right now during class. Just take the survey. Just go in and answer the questions so that Thursday I can release the data and then show you how to use it, because there's a little bit of confusion. If I just release, so don't work. If all of a sudden you see that the data has been released, don't work on it till I tell you about it, because there's a couple of things that if you don't recognize what you're doing, you're going to have to redo all your work anyways. So don't dive into it yet. I will talk about it on Thursday. One of the things that happens is that the question number and the answer number are off by 1. It's kind of the same way that programming works, where programmers oftentimes start counting at 0 in programs. Whereas normally in real life, we start counting at 1. So the way they programmed this was the question numbers have 1 number, and then the answers are off by 1. It's like the programming, because you start at 0 sometimes in programming if you have an array or something like that. So what that means is your answers are often off by 1, or they will be off by 1. So when you go in there, if you look at question number 8 and then you look at column 8, you're actually looking at the wrong answers, right? And I see this when even though we talk about it extensively, I see this when people are giving me their projects and I'm watching their video and I'm going, oh, this person doesn't even realize that they're presenting data for a different question than they think they are. And that, it doesn't look good in your project when you don't even realize that your data doesn't match, because usually it's kind of obvious. Like, don't you like, there should be that questioning, right? A lot of times there's this idea that if it comes out of a computer or if it's on a screen and it's mathematical, I can trust it. No, not at all. Hopefully that's a lesson that many of you are picking up in statistics, which is you have to ask yourself, does this make sense? Does this seem right? I mean, that's one of the things about statistics, is it can be used nefariously. So you always have to be very skeptical of statistics and ask yourself, wait, do these numbers seem right? Does this make sense? And sometimes it does. Sometimes the data comes out in a way you didn't expect. But if the data is coming out in a way you don't expect, you look at it, right? Don't just blindly go, I don't know, there's numbers on the screen, so I'm just going to find the mean, and then I'll make a histogram, and I'll do the thing. And then I'm sitting there looking at it going, you have no idea that your data is completely for the wrong question. Like you never stopped and analyzed it enough. It doesn't go. It's definitely going to hurt your grade. So I will go over all of that on Thursday so that you can make sure that you're looking at the right answers to the right questions and not getting confused about it, and mixing that up. And then we'll talk about what to do with everything, and then you can move ahead. At that point, I will take these 2 unpublished assignments to do with the project, and I will open them up. The good news is neither one of them is very hard to do. So here's what I'll recommend. On Thursday, these should be open and have better due dates. Obviously, I can't give you something that's due on the 28th if I'm not going to open it till Thursday. So these due dates here will be adjusted to more realistic due dates to give you a little bit of time to work on it. And here's what I would recommend you do. Try to do this work on your own, right? Again, what you should not be doing in your groups is splitting up work and going, you do this part, you do this part, you do this part. What that means is that each of you only does about 30 to 40% of the material, and then you don't understand 60% of the material. And trust me, it shows in your project. Right? So what you should be doing is everyone goes in and does their survey question summaries. That's basically you figure out your mean, your median, your standard deviation, all that kind of stuff that we talked about, those early summary numbers, to just give you an idea of what's going on with your questions. Right? StatCrunch does all that for you. I've shown you that before. We can look at it again. Once the data is released, it's real easy to do. You'll post your stuff in here, and then you'll have that part of your project done where you've made your summary stats, right? So it depends how organized you want to be. I would recommend just create a folder somewhere in your computer or thumb drive or online file storage, whatever it is that you personally do. Create a file, and as you're doing these projects and you go, oh, I like this. This is the one I want to use. Stick it in that folder. And then when you come back in another, whatever it is, 12 weeks or something, it's less than that already. We're almost halfway through the semester. So in like another 8 weeks, when you decide you're ready to start putting your video together at the end of the semester, you've got a folder of everything. You don't have to go back and redo it or find your stuff. It's just right there in a folder. Oh, here's my visuals. Here's my summary. Here's my correlation. You have all that stuff ready to go. Okay. And I'm going to keep saying this, and I know sometimes you go, why does he say this every time? Because I still get emails from students who are confused about it. For both of these, as all of the project stuff in this class, you have to leave a post to get credit, right? I'm trying to say it as simple as I can. You can't, I'll get an email, oh, well, so-and-so, I'll just make up names. Oh, Sarah left a post and she said that me, Jen, is her partner. Why didn't I get credit? Because it doesn't. Like the first line in these is generally every person must leave a post to get credit. Okay, so it goes along with that thing. You shouldn't be dividing up the work in your groups, and you shouldn't be deciding who's going to post. Everyone should be doing all the work. Everyone should be leaving a post in order to get credit for these. Okay. So you'll go in, you'll do that. Everyone's going to do their stuff, and then you'll have that part of your project. Like at least the math part will be done, and then you can just worry later about creating your actual video. We'll talk more about how to create the video as we get closer to the end of the semester. Most of you probably shouldn't really be worried about making the video until we're, maybe a week or two ahead of finals. Then some of you might start working on it. Maybe around Thanksgiving, someone's like, I think I'm a little bit ahead. I think I'm ready to go. That's one thing, but that's still a little ways off. And then you're going to do your project visuals in StatCrunch as well. So here's what I think you should do if you're trying to do a good job on the project. Do this stuff on your own. Create your own project visuals. Go in, make a histogram. Play around with the histogram. Play around with the bin sizes. Play around with different stuff and look at the different histograms that you can create. I'll talk about that on Thursday as well. Histograms, whatever diagrams that we've learned in this class that you think are appropriate, go in and try some of those. But don't just go with the first one you make up, right? You might make 5 histograms for the same problem where you just change the settings a little bit, okay? And you might go 5. Well, I'm going to have 5 histograms. It'll take you less than a minute to make 5 histograms, okay? And then you can go, ooh, this third one, that looks really good. I like the way that this is going to fit with the narrative that I'm trying to tell in my video. I'm using this one, right? Don't just go with your first one. Then what you should probably do is everyone does that, like everyone in the group will already do this work for these 2 problems. Then you get together in your group and share, and probably someone in the group will have like done a really good job on certain parts of this, and then they can share and you go, oh, I thought I had a good histogram, but your histogram looks really good. What settings did you use? And then you can all help each other through that, right? You can talk about it, and in that process, you're actually going to learn more. You're going to get better at it because you're discussing it, especially since you've already tried it, okay? The person who shows up to the group and hasn't tried any of this stuff and is just sort of trying to write everything down from the work that other people did, you're not going to gain much because the other people already have a high level of knowledge because they worked on it. And then when they get a hint or a tip from someone else in the group, they're able to make that next step because they have like a base to stand on. They have a basic understanding of what they're doing and go, oh, I know what you did. You used a bin size that was this, huh? Yeah, I used this bin size. Oh, that's really good. And it's all going to make much more sense than if you're showing up empty-handed and going like, I hope no one notices that I didn't do any work. They're going to notice, right? It's pretty obvious. It's obvious when I'm doing the videos at the end of the semester who's done work and who sort of like tried to use the work of other people in the group, because it's, in a video, it's obvious if you know what you're talking about or not. You're not going to fake your way through the video. So basically do your work ahead of time. I'm not saying you have to spend hours and hours on it, but honestly, if you spend 30 minutes on each of these pieces before you meet with your group, and then you meet with the group, and then you talk about stuff, you're probably all going to end up with really good stuff here that'll look good in your video. So that's my recommendation for how you do it. The wrong way to do it is to break it up and go, okay, you do the summary questions, you do the project visuals, I'll do correlation, because again, then that means that each of you only knows 1/3 of the material, and 2/3 of the stuff you don't know what you're doing. Right? So you should, and StatCrunch makes it so easy. In the old days, you'd each have to make your own scatter plots by hand. That would take forever. Now it takes seconds, right? So why not just do it on your own so that you understand what's going on? And plus, if you've worked on it on your own, that means at the end of the semester when you go, I liked this histogram, but I kind of want it a little different, you're going to know how to go in and make a different histogram that you want to mess with, right? That you want to change a little bit. So we'll do all that on Thursday, whether people sign up, whether more people do the survey or not. I'll release the data because at some point I just have to release it. But I'd like to see it be easier for everyone if we can get a few more people to do that survey. So again, if you haven't done it yet, just do it right now during class. Just go click the link, go take care of it. Okay? And then I'll give you realistic dates for these. Okay, that means, as you can see, we're kind of moving into chapter 4 here. So you still have, you have a reasonable amount of time to work through chapter 4. And the big thing we're going to be looking at is correlation. Correlation, in my opinion. Oh, before we go on to correlation, is there any questions? Does anyone have a question for me? Any comments or questions, or anyone want to speak up about anything? Okay. Anyone who wants to talk to me, you're welcome to talk to me after class as well. Also have office hours after class, so feel free to come in and talk to me at that point. Okay, correlation. Correlation is one of the most important topics of statistics. I also think it is one of the more interesting topics because, let's see. It's just a lot to take in right now. Someone's saying, yeah, it's a lot to take in right now, right? Because the statistics class, it moves quickly. Unfortunately, November is going to be right around the corner, and then we're sort of at that point getting towards the end. But yeah, it's a lot to take in. So remember, you're welcome to come talk to me in office hours. Talk to your groups, and if the group has a question, come talk to me. And you can talk to me without going to your group, but I'll tell you, the groups that really do well are the ones that they work on the material themselves. They work as a group. If they have questions, they come talk to me. And then the questions are, we get through it really quick because you've already worked on it so much, you understand most of it, and then we move it through. So that's generally the most successful way of doing it. But by all means, if you have questions or concerns, or even if you're just stressed out by the class, come talk to me, and I will try to help you with it. Okay, so don't just sort of suffer in silence where you're getting overwhelmed. Come chat with me in office hours, and we'll see what we can do about it. Okay. Right. So let's see. What do we got here? Correlation, very important idea. It seems real simple. And in some ways it is kind of basic, but I think people have a tendency to oversimplify it because it is more complicated than it seems at first. And people miss the subtleties of correlation. And this is one of the ways in which it is very easy to give people wrong interpretations of statistics, right? So this whole thing that I've talked about, ethical statistics versus unethical, a lot of times you're listening to politicians and news and stuff like that, and what you'll hear is completely incorrect statistics, but 95% of the people listening to it don't have the skills to go, wait a minute, that actually sounds like it's being used wrong, right? You want to be in that group of people, and you should be after this class. You should be able to be in that group and go, wait, what he just said, sometimes what people are listening to flavors their opinion of a thing. Even if it's a politician you like or a news show that you really like, you should still call them out when they get it wrong, right? This is one of the I won't go into politics, but one of the problems with our country, we don't call out our own team or whatever person it is that you like. Like if you're on a certain side of politics and that person is using statistics incorrectly, you should go, okay, I agree with your overall idea, but what you just did is wrong. Your idea here is incorrect. Okay, that statistics doesn't really support what you're trying to do. We do this on campus when we're working on certain projects. A lot of times we have data because we always try to be data driven. But sometimes in other departments where people don't understand statistics as deeply, they'll bring in something and say, oh yeah, well, we'll use this to support the data. And then, some of us will go, well, I agree with what we're working on and I agree with where we want to get, but these stats don't actually support what you're trying to say. They seem like they do and they seem close, but it actually hurts our case if we use bad statistics, right? It's like if you're in an argument with someone and you try to make a point and then they shoot that point down, your side looks bad, right? It doesn't look good. You want to have solid evidence. You want to be able to say, no, this statistic supports the view that I'm trying to make. So, you just want to be skeptical about statistics. So correlation, let's look at so what I did here is I found this textbook right here is called Triola. It's one of the most, It's one of the most used statistics books it's probably the most used statistic book in the world. It's not the one we're using for this class because the book that we're using for this class has this really good online integration with the videos and the lessons and that kind of stuff. And we've actually shown it's better for students in an online class. But sometimes it's hard to go look things up because you have all these videos. So I just looked up, this was posted by a professor, so I haven't had time to look. I'm not encouraging you to do any kind of piracy or anything, but I just Googled Triola book or something like that and found a PDF of an old copy, not the current copy, but like it's a little bit older. But these definitions aren't changing. So I think this will help a little bit. I can show the definitions on the screen while we're talking about stuff. So here's our definition. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. Notice two words that never occurred in that sentence. Cause and effect. You never saw the words cause and effect in that sentence about correlation. And yet there is something about the human brain that as soon as we see a correlation, our brains instantly jump to cause and effect. The truth is that in reality, there is almost never a single cause with a single effect. Because if something is that easy, then you don't need to study it, right? Like, okay, so cause and effect, real simple to follow. I have a glass of water. I dump the glass of water on my head. That's the cause. The effect is that my head is now all wet, right? Pretty basic. Cause, dump some water. Effect, I'm wet. But do we need to study that? Do we need to look further and go, okay, why is his head wet? What occurred? Was it the fact that he dumped water on his head? It's pretty obvious, right? So when you have something that's a single cause with a single effect, it's generally obvious and you can see it. That almost never happens in real life. What usually happens is there are a lot of factors to things, and this is why it makes it so complicated to come up with solutions, because there's lots of things impacting things. I could teach in a whole course where we just talk about social issues and the fact that, a lot of times people look at social issues and they boil it down to, well, the problem with this is this. Well, okay, but that's a very oversimplified view. Usually there's a lot of things affecting a lot of our social issues. And so if you just try to pin it on one thing, you're missing maybe 80% of the problem, right? And it's one reason that we have trouble fixing things. Take, for example, reading levels, right? We can look at different schools and we can see, well, in this school over here, reading levels are above grade level. The average student in this, or the average reading level at this school, the student is above grade level. So maybe they're in the 5th grade, but they're reading at almost a 6th grade level. Oh, and then this school that's one city over, well, they're reading on average below grade level. So if they're in the 5th grade, maybe they're reading at a 4.2 grade level or something like that. If you go in there thinking that there's going to be one cause to that, it's going to be useless. You're not going to be able to get anything done because there are lots of things that affect reading level, right? There is the money, the amount of money that's going to that school, the amount of money that the parents have in their personal lives of the students that go to that school, the resources that the school has, right? The teachers, there's a little variation in teachers. Sometimes you get a really great teacher. Sometimes you get one that's maybe not as good. There are lots of things that go into that, and some things that might not even seem like a big deal. The way buses run, right? If you get your buses to run efficiently and you get your students home in a fast manner, they have more time to sit down, get into their homework, and start working on it. Whereas in another place, if there's fewer buses, so the bus routes are longer, and some students don't get home for over an hour, well, that's a lot of time they don't have to study now because they just spent it sitting on a bus, right? So all of these things, there's most things that are interesting in real life do not have a single cause followed by a single effect. What you have is multiple causes which affect the outcome. So that's why in here we never use the words cause and effect. But it's really hard, and you'll find yourself doing this. We read something and we instantly say, okay, thing A causes effect B. But it's not that simple, right? So just be aware of that, right? In some of these books, they'll have like in big bold letters right after we define correlation, like giant letters, you'll hear the phrase, correlation does not imply causality, right? And you'll hear me say that numerous times throughout this semester. Correlation does not imply causality, because causality means, A causes B. If I dump the water on my head, we know what's going to happen. My head's going to be all wet, right? That one's very simple. A causes B. But in real life, anything worth looking at, it's harder than that. Then go back to the examples we gave a while ago. There's a strong correlation between ice cream consumption and shark attacks. But it's very obvious that eating an ice cream does not cause a shark attack, and getting a shark attack does not cause you to go eat ice cream, right? Neither one of those variables have an association. There is a strength between those. As one increases, the other one generally increases. However, there is no cause and effect in there. So basically for this entire class, if you start thinking about things in terms of cause and effect, just stop and think about it for a minute, because in almost all cases, you probably do not have a cause and effect relationship. There's probably more variables involved. Like we talked about the one with number of automobiles you own and life expectancy, right? You can't manipulate one of those and think it's going to cause the other to change. Oh, you live to be, what do they call them? Centenarians, where they people that live to be 100. Oh, you live to be 100? You must have owned a lot of automobiles. No, that doesn't necessarily hold up. Like, it's not cause and effect. But in general, people who live longer have more automobiles, but that's just because money is that variable in there that is the main cause. It's not the only cause, right? You can have lots of money and still die early, right? So again, even there, it's not just one variable controlling things, right? So you might go, well, man, he's really spending a lot of time talking about this. This is one of the key features, and it's hard for students because I'll still hear them when they do their regressions and correlations talking about cause and effect. You shouldn't even be using the words cause and effect, probably. Talk about correlations, and we'll get into, how to do all that. All right, a linear correlation. Here's another one where people oftentimes make assumptions. Just like up here, they assume that a correlation is a causality, and they make a bad assumption. Same thing here with a linear correlation. Sounds very easy, but people oftentimes assume that things are linear. So a linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. That sounds confusing, right? Basically what we're getting at is, where is it? We'll come back to this picture in a little bit, but see this? See, we have some data here, and that line kind of fits our data. That's the game we want to be playing here. That's our goal. We have these data points, and yes, they're not perfectly in a straight line, but we can create this line that more or less captures the behavior of our data, right? This is what they mean when they talk about a linear correlation, this right here, that we can put a line through it. We can calculate a line of best fit, which, good news, the technology is going to do it for you. And then you have your line, and you graph it and go, yeah, that looks pretty good, right? That's a linear correlation. That's what we're talking about. So where's the tricky part here? The tricky part is that, again, the human brain, people seem to have this thing where they assume everything is linear. Any kind of relationship that they are handed, they immediately assume it's linear, right? I see this as a professor. I see this all the time happen in society, where someone makes an assumption. I just heard this. I'll give you the example in a second about earthquakes. I heard a conversation the other day. I don't know if it was on the radio or something, but they had no idea what they were talking about because they were assuming a linear correlation for earthquakes, which the way we measure them, which is not how it works. So we mainly teach about linear correlation because this is an intro to stats class, right? You can't learn everything right now, and many things have a linear correlation, so we want to know how to use those. This is where your y equals mx plus b is going to come into play. A lot of you who took algebra, much of your algebra isn't going to be any good to you in this class. We're not going to factor. We're not going to do operations with logarithms and stuff like that. But you need to be very comfortable with your y equals mx plus b in order to understand this chapter. So that's the one thing you definitely need to know. If that's scary to you and you go, oh, I haven't looked at lines in a long time, I don't remember, just find a 5 to 10 minute YouTube video on slope intercept form or y equals mx plus b form, whatever you want to look up on YouTube. Just watch a little video on it and remind yourself how it works. Okay, because you need to be comfortable with lines, or this whole chapter you're just going to be sort of like stabbing in the dark trying to hit your mark. Okay, so don't assume you have a linear correlation. Oh, the example I was going to give, I think it was on the radio. I was driving around listening to the radio the other day, and people were talking about earthquakes. So the way we measure earthquakes, and they were talking about like, oh, well, like here's kind of the idea. Okay, the biggest earthquake I've been in, I think, was a 5.4. That one we had in Ventura a few years ago. Some of you were probably in school when it happened. It was a 5.2 or 5.4 or something like that. And you go, oh, okay, well, that was kind of a little bit alarming, but it wasn't a terribly big earthquake. It didn't like destroy things, but it definitely got everyone's attention, especially if you were in the earthquake was actually in the ocean, but if you were relatively close to the coast, like I was at the college, you definitely felt it. No one was going to not feel that thing. And they start going, okay, if I was in a 5.4 and I just heard about this other earthquake that's a 6.2, and they think about it linearly, like, okay, well, that shouldn't be that much worse, right? A 6 is a little bigger than 5, right? And then a 7 is a little bigger than 6, so a 7 shouldn't even be that bad, right? And then like an 8, you hear about these 8s like, that we've had in Nepal that like basically all you see is rubble. There's like not a building left. Everything's just, rock on the ground. You go, how could a 7 be that much worse than a 5.4? It's because in their heads they're thinking linearly. They're thinking, well, 7's a little bigger than 5. In reality, the way we measure earthquakes is logarithmic, which means every time you go up 1, it's a factor of 10 bigger. So a 6.0 is 10 times worse than a 5.0. A 7.0 is 10 times worse than a 6.0, right? An 8 is 10 times worse than a 7. So when you're thinking about it linearly, you go, I don't know, like a 8, shouldn't that kind of be like half again as bad as, it should be like 50% worse than a 5.5 or something? No. In fact, it is something like 120 times bigger than that little one that we felt in Ventura, right? Which was, it was little compared to the big ones, but still kind of alarming to some people. When you go up by 1, it's 100 times worse. So that's what I'm talking about when I say people make these assumptions that they're dealing with a linear measurement when actually they may be dealing with logarithmic or exponential or something like that. So that's why it's actually really important that we make this distinction about a linear correlation, because then we actually know what we're dealing with, okay? So where are we? Right. So the way you make a scatter plot is that you need 2 pieces of data. One will go along your x-axis and one along your y. So each individual, right, this is the one I give it as an example sometimes. Let's say on the survey that everyone takes, I don't remember the questions that were on the survey, but let's say shoe size and let's say height, okay? So when you answer the survey, you're one person, but you answered a question about height, you answered a question about shoe size, right? So what we can do is we can take your data specifically and we can mark, here's where their shoe size is. Here they're doing centimeters. So it's like not the shoe size where you say like, oh, I'm an 11. It's like whatever centimeters the shoe is. But we would mark that. And then the y-axis would be your height, whatever you answered for centimeters. And then that's how the dot is created. So it's that's why you need 2 quantitative questions in the survey. Is you need 2 of them, because otherwise you're not going to be able to make a scatter plot, right? Because you'll have an X but not a Y because you didn't ask the right kind of questions. So you need to find your quantitative questions, and then you can plot everyone. I mean, StatCrunch is going to do it for you, but you should understand what you're doing, right? And you can choose, do you want shoe print to be the x-axis and height to be the y-axis, or do you want it the other way around? Depends what you're trying to do, right? So that's what our scatter plots will look like. Okay, well, your scatter plots can have different shapes, right? So remember we talked about, so there's this correlation, means there's a connection between these two variables. Well, it'd be really great if we could measure that, right? It'd be great if there was a numerical value we could assign to how strong a correlation is. If two variables have nothing to do with each other, we want to be able to measure that. If two variables are very, very closely related, we want to be able to measure that, right? So what you do is you look at your scatter plot, and then the first question you should probably ask is, does this thing look like it's linear? Well, this does. You could imagine a line going through this data right here, right? Drawing a line through there. Well, that's what we're going to be doing here in the near future, is making a line that goes through here and describes this data. Sometimes called the least squares line of regression, sometimes called the line of best fit. It goes by a lot of different names. It's all the same thing, and StatCrunch is going to calculate it for you. But you have to be able to remember what slope and intercept are so that you can interpret your line of best fit and know what those things mean. Slope and intercept you definitely need, right? And when I see people bring those up in their videos during the correlation, I go, oh, this person knows what they're talking about, right? It sort of gets my attention a little bit. This one over here, yeah, you can imagine a line going through here, but it's not quite as clean as over here, is it? Here it's pretty, you can really come up with a line that goes through there, and you'd probably be pretty close to the actual one. Here it's kind of hard to tell, I guess, maybe through the middle, but it looks like things are spread out a little bit. Well, we want to be able to come up with that, because if you give StatCrunch a scatter plot and you say, give me the line of best fit, it'll do it. It'll calculate it. It may be a terrible line of best fit, but it'll give it to you. So what we want to do is look at this thing called an R value that tells us how strong that correlation is. Okay, so R, very important idea in statistics. In fact, there was a programming language written specifically to do high-level analysis using statistics. The name of that programming language is R, the letter R. So any of you who are interested in it, I think it's probably freely available. You can just Google it, R statistical language or whatever. It's just the letter R. That's how important this thing is. They named the whole programming language after it. Okay. So what this is our correlation coefficient. It goes by a couple different names, but it's a measurement that measures how close, how tight is your correlation, right? Is it just doesn't seem to have anything to do with anything, or does it look like these variables are really closely related? And the scale seems a little bit weird. You can have a negative R value, or you can have a positive R value. They go between -1 and +1. So it takes, I wonder if there's a picture in here. I forget. This is the older version of that textbook, so sometimes the texts are a little bit different. Doesn't look like they have one in here. They must, though, right? Oh, here it is. Here's one. It's not so pretty, but so we have -1 on our scale here, +1 on our scale over here. So R can take place anywhere between -1 and +1. But if you're near 0, we measure that as being either a weak or not a real strong correlation. Okay. So like we'll go back in a minute and we'll look at those R values. The one where R value was 0, you're not going to come up with a line through that graph. It's like, it won't make any sense. People will look at your work and go, well, why didn't you pick a different line? Why not this line, right? So the closer you are to 0, the weaker the correlation is between the two variables. And they've sort of arbitrarily picked a critical value. Don't use these values right here, because sometimes you might have an R value of 0.85, and it's still a pretty good correlation. So the closer you get to 1, you have what's called a positive correlation. The closer you get to -1, you have what's called a negative correlation. Now, what does that mean? A negative correlation? They literally just mean the negative sign, because this is actually going to be your, well, no, That's not exactly true. Let me rephrase this. So the closer you get to 1, that means that there's a tighter connection between the two variables, which means as one goes up, the other one's going to go up. Or as one goes down, the other one's going to go down. A positive R value means they move in the same direction. Now, you can have a value, your R value over here close to -1, but they're going to go the opposite direction. So they could be really closely related, but go in opposite directions, right? So sometimes that happens where you have like sound levels, right? Like the more you increase your distance from a speaker, the lower the volume seems, right? There's going to be a direct correlation. If there's a speaker, outside and you're 10 feet from it, every little bit you get closer to that speaker, it's going to get louder. So your distance is decreasing, but the loudness is increasing. And the same exact thing, if you start to back away, you're increasing your distance to the speaker, but the volume's your perceived volume in your head is going to go down, right? So in that case, you'd have an R value really close to -1. Like if you were taking measurements of the perceived volume and the distance from the speaker, your values would be really close to -1, telling you there's a very strong connection between distance from the speaker and perceived volume, but they go opposite directions, right? As one of those variables goes up, the other one goes down. That's all that means. A negative correlation doesn't mean anything bad, and it doesn't mean you don't have a correlation. It means those two things are going opposite directions, whereas over here, they're going the same direction with each other. Okay, so let's go back and look at those graphs we had up here. Right here. So this one, see how that correlation's really close to -1? This is a pretty strong correlation. And look, as our X values increase, so we move to the right on the X-axis, our Y values decrease. Those variables are going opposite directions of each other. Here, we have a positive correlation that is high, but you can see this is starting to get kind of scattered out. Our line is not going to represent it as well. But as the X variable goes up, so does the Y variable. They're going up together. So notice that this R value is approaching 1, right? So you want to know the difference. It's kind of like slopes, right? If you think about your slope, you know, in your head, whether it's positive or negative, you can decide whether it's a line like this or a line like that, which way it's going. Look down here, correlation 0. Let me move this a little. Correlation 0. There's no association between our X and Y variable. So you can't make any kind of predictions. You can't control anything. There's no connection between these two things, okay? So that just looks like a random scattering of points, right? If I said, okay, everyone draw the line of best fit through here, we're probably going to get 35 different answers because there's no real good answer for what the line of best fit should be there. And then here we have something, this is where you have to be tricky. Remember I talked about assuming a linear relationship? If you have data like this, which is pretty clearly, that looks to me to be quadratic. If you tell StatCrunch or some other piece of software to calculate your line of best fit and to give you an R value, it will do it, right? It's not going to go, wait a minute, are you sure? I think this data is quadratic. Like StatCrunch doesn't do that. You told it to carry out a function, and it will. So you can get a line of best fit. It's probably going to go something right through here. And then you've got your R value, which isn't great, but you're going to get your line through here. Well, I'll make that point in a second. But that's why you have to recognize, oh, this isn't linear data. I should not be trying to use a line of best fit on it. You have to look at it. Again, common sense, right? StatCrunch does a lot of the number crunching for you, but that means you have to be a little bit alert and paying attention, because if you tell it to do something, it's gonna return what you asked it for. But if you try to use a line of best fit here, you're gonna look like you don't know what you're doing, right? People are gonna kind of stop reading the whole thing because they're gonna go, this person doesn't even know what a line is, and they're trying to talk to me about statistics. Right, so whenever you're dealing with correlation, you have to do two things. You have to check the R value and think about it on that little scale we talked about. But also the second thing, and this is pretty easy to do, just look at the data. Right, some people get trapped in just trusting blind faith in the R value, just look at it and go, oh, that's not linear. Because we can come up with examples actually like this. Like in this case, it's a bad fit, but we have a bad R value. But we can come up with cases where your R value is high, but your graph looks ridiculous. So you really have to do both. You have to check the R value, and then you just have to do a common sense check of looking at your data and going, does what I see logically match the R value? Yes, it does. Okay, then we're good to go, right? You got to check both of those pieces when you're doing it. Okay, where are we? Yeah, we talked about the R value. There's your little chart again. You can find these on the internet. You just look it up, a correlation chart or something. Let's see, is that? There's more details you'll pick up when you watch those videos, but and then they get into hypothesis testing. We're not doing that yet. They get into the pieces you're going to need to do. So let's jump over to this other page I had pulled up so you can kind of see a few more examples. So basically what's going to happen is, you're going to look at your data and you're going to have numerical, quantitative data, hopefully 2 questions. Hopefully you ask 2 quantitative questions, and you'll have them right here. In this case, height and weight. So in general, you would expect that people that are taller are probably a little bit heavier. That's not always true. You can have, you can have someone who's tall, like, definitely tall, like, 6'5", 6'6", something like that, but then just super skinny, right? Doesn't really have much muscle, very low body fat, probably in single-digit body fat, and they don't weigh as much as you'd expect for someone who's that height. And you can have someone who's short, who has, a higher percent body fat that might weigh more than that tall person. But in general, you expect as people are taller, they're probably going to weigh a little bit more. That's why we don't get a perfectly straight line. We kind of get these values that's why we call it a scatter plot. They're kind of scattered about, okay? So then you would, you can just look at your data. So this one is what, ice cream sales versus temperature. So this makes sense. The hotter it is, the more ice creams are going to sell. If you try to sell ice creams in January in New York City, you're not going to sell very many, right? So what we ultimately like to do is create this line of best fit. StatCrunch will do it for you. Your TI-84 will do it for you. There's probably websites that will do it for you. But notice we took that same data and we put a line through it. Now, someone didn't just draw this line and go, oh, I think that looks like a good line through the data. You calculate it using the line of best fit, also called the least squares regression. It goes by a number of different names, but it's calculated, and then you graph that line. Well, when you graph that line of best fit, the slope and intercept are actually really helpful because remember the slope of a line is the rate of change? Well, the slope of this line of best fit tells you, like, okay, so for a 1 degree temperature change, how much do I expect my sales to go up? And you can make predictions for it, right? So if you're like, oh, I was supposed to take the day off. I wasn't going to open the ice cream shop, but it's like 10 degrees hotter today. You're like, man, if I don't get in there, I'm going to miss out on like an extra like $350 worth of sales or something because you can predict roughly. Like you're not going to get it exact, but you can predict roughly, well, it's 10 degrees hotter today. Probably going to sell this many more ice creams, and you want to get in there. This line of best fit is really helpful for making approximate predictions. Okay, it's not perfect. Just like you could imagine up here with height and weight, if I know someone's weight, I cannot perfectly predict their height, right? Or the other way around. If I know someone's height, I can't perfectly predict their weight. There's going to be a range of weights. But if you give me someone's height, I can probably come up with a reasonably good guess for their weight if we had the line of best fit. It'll be off sometimes, but it's also a reasonably close guess. So you can use that line to make predictions about stuff. Very, very helpful. And then most data is like this where you have lots of data. Oops, that showed up before. Yeah. Lots of data here. kind of seeing an overall behavior looks linear. So we make a line of best fit going through there. Again, we don't do it by hand. The line of best fit is a very specific calculation, and it is not fun to do by hand, even if you have a dozen data points. It gets kind of tedious calculating the line of best fit. The good news is StatCrunch is going to do it for you, and then you can create that line of best fit and go from there. Then we talk about extrapolation and interpolation and all that kind of stuff, which we'll talk about next time. Okay? Don't want to get into it now. So start working on that stuff. Those of you who have not taken the survey, please do it. Please do it. At this point, every single person that we have taking the survey is going to make your interpreting your data a little bit easier. All right. So please do that. So like always, I'm going to close down the YouTube stream. Anyone who wants to talk to me, stick around in Zoom and talk to me about, whatever appropriately related topic you want to talk to me about, and we'll talk about that. Otherwise, I'll see you in a couple days and we'll move forward with stuff. Okay, thanks everybody.